Hello, Dhananjay. Are you here? With me? Hello,
Hello,
Dhananjay. Hello.
hello,
Yes, you
hello,
can.
Naren.
Yeah, you can start. Good to.
Okay. I'm starting the lecture. Well, hello everyone. Uh, so today's lecture will be about ordinary differential equations. Okay. So I'm sharing my screen. So how do we solve ordinary differential equations in MATLAB? Okay. So we will look how to solve these equations. Okay, so we know d of our ordinary differential equations look like dy by dt equals to function of t comma y. Okay, and let's just initialize y of t0 equals to y0. Okay, so the here f of t comma y is the slope of the function, okay, and the output and the result is y initial value, y of t0 is y0 initial condition. We know this thing, we know. Okay, dy by dt equal to function of t comma y and y of t0 equal to y naught. Okay, so we know from mathematics that limit h tends to 0, y of I plus 1 minus y of I divided by h equal to function of t comma y. Okay, the same equation dy by dt can be written in this form. Okay, so by multiplying h with f of t comma y and adding y of I, we get y of I plus 1 equals to y of I plus h into f of t comma y. Okay, so this method, so we find means we vary the value, means we make h very small and find every value of I y. Okay, at every iterations. Then we plot all the values of y and get the final curve. Okay, this was the main method of finding y. Our main motto was finding y. Okay, so this is how we do. This method is known as the Euler's method, or perfectly we know Euler's explicit method. Okay, y of I plus 1 equal to y of I plus h into f of t I comma yi. So how we will do in MATLAB, I will show the code. Okay, let's just take example what ordinary differential equation y dash equal to minus 2t y with initial value y of 0 equals to 1. What will be the analytical solution? Means what will be the analytical solution? Y of t equal to e to the power minus t square. By mathematically we are finding this. Okay, so in this method we can have different value of h. Okay, 0 0.1, 0 0.01, 0.001, this type, and we get corresponding value of yi. Then we plot yi with t. Okay, so I'll so this is the MATLAB code which you are seeing. Okay, solving ODE using Euler explicit method. Y dash equal to minus 2t y. Initial value of t is, means the range of the range will be t0 equal to 0 and t end equals to 5. Okay, up to t0 to t end we are plotting the curve. Okay, we want to get the graph. Okay, now here we are initializing value, means t0 equal to 0, y0 equal to 1, t end equal to 5, h step size is 0.1. Okay, So the total number of values which we will get is n. Okay, n is equals to t n minus t0 slash h. This will be the total number of values of yi which we will get. Then we will plot yi with ti to get the whole graph of yi. How we will do it? Let's just see. These are the given values. Okay. Now we are initializing our solutions. What will be the t? T equal to t0 is to t0 is to h is to t end. Okay. This code, I think you know how it will give its output. It will give output like this. What was the value of t0 is 0. So it will give 0 means 0. Then it will give 0 0.1. Then it will give 0.2 like this. Okay, like this it will give its values. So we are means we are inputting every value of t to get the corresponding value of y I plus 1. Okay. So these are the method. Means this is the equation f of I equals to minus 2 into t of I into y of I, and y of I plus 1 will be nothing but y of I plus h into f of I. H is the step size. Okay. And this is the plotting of the graph. Means we got every values of y and we got every values of t. Means t we have initialized. We have initialized like an array. Okay, let's just MATLAB run the code. Then we will see the graph. Just it plots. Okay, means it is plotting all the values of t with the corresponding value of yi. Okay, here you see it is plotting t versus corresponding value of I. We have every value of t means t0 to t end means t 0.1, 0.2, 0.3, 0.4 and the corresponding value of y. Okay, how we got? By using for loop. For loop ran from where to where? From 1 to n. What is the value of n here? N is 50. So 50 times it gives the value. It gives the value 50 times. So we are plotting it and getting graph like this. Okay, this is the graph of y of this equation. Y dash equals to minus 2ty. This is how we do by Euler's explicit method. Okay, we can vary the step size also. We can vary the step size. Let's suppose the less the value of h, the more the value of yi we will have. Okay, let's if we take y equal to h equal to 0.01, we will have n equals to 500. Means for 500 values of x, at 500 values of t, we are getting the corresponding value of yi. Here, see the graph. The graph will be the more accurate than the previous one because we are having more values of yi. Okay, so this is Euler's explicit method. So is there any means this is the code. Okay, so is there any MATLAB function in MATLAB function which we can directly use to get the graph of the ODEs? Yes, there is. What this code is? This code is known as ODE45. By using ODE45, we can get directly the solution of the differential equation. How to use that? How to use ODE45? I'm just showing it. Okay. So for using ODE45, you have to write this syntax. Okay, here t sol and y sol are the corresponding value of t and y, and here you have to write at the rate t comma y, ODE fun t comma y. ODE fun is nothing but the function name in which we are passing variable t and y. T0 to t end is the interval where we want to plot the graph. Means we have to give the interval from where to where we have to plot the graph. What the values we have given here is t0 equal to 0, y0 equals to 1, and t end equals to 5. Means t0 equal to t0 equals to 0, t end equals to 5. Okay, what is this ODE fun? What does ODE fun is? ODE fun is nothing but a function name. Function name which gives the output dy equals to minus 2ty. Okay, and here we have to initialize the value y of 0. What we have initialized is y of 0 is 1. Okay, this also gives the same result. What is the main means ODE45 has different algorithm, means it solves ODE by different method. It solves ODE by RK4 method, not Euler's method. H is not constant value. H is not constant value means uh, it just means approximates its values. Means it takes its own values according to the equation. It may take 0.1, it may take 0.001, etc. Okay, it itself computes the value of H to have a better solution. Okay, that's why ODE45 is more accurate. So if we just run the code, Control C, we can have the graph directly. See, we have the graph the same as that we have got previously by using Euler's methods. Okay, so I think these two things I want to have in this session. Suman, are you listening?
Yes, I'm there. Am I audible?
Yeah,
Yes,
yeah,
yes, you are.
you're audible.
Okay, okay.
So from here, Suman can carry. If there is any doubt, you can ask regarding the code. Okay, Suman, I think you should
Go ahead.
go ahead.
Okay, thank you, Venodar. So let me share my screen. So today I'll be discussing with you guys. Okay, am I audible?
Yeah, Suman, you
Yes,
are audible.
yes.
Yes, sir.
So today I'll be discussing regression and interpolation. So let's go ahead. So let's say we have two data, that is x and y. Let's suppose this is the data. So what does regression do is that it obtains a straight line that will best fit this data. So let's assume that this is the function that we get after regression, y equals to 0.45 plus 0.47x. So this is regression. We want to fit, I mean, we given a data, we want to fit the best line. Now, what is interpolation? Interpolation is basically just join the dots. Like whatever the data points we had, what does interpolation do? It will, draw a curve passing through all these points. And after we get a curve like this, what we can do is that, suppose we have this point that we already know, but we don't know the value at this point. through interpolation, we can know the value at different points that we were not knowing beforehand. So for example, let's say after we did this interpolation curve, at x equals to 2.0, we get the value of y as 1.87. So this is the difference between regression and interpolation. So now we will be looking into regression techniques first hand. So we will start with linear least squares. This is the most common and famous among the methods. So let's say we want to fit a straight line y equals to a0 plus a1 of x. And this is the given data. This is the x points and these are the y points. So what is the least squares does is that it actually tries to minimize the error. I mean the square of the error. Like over here in our case, our error will be y minus of a0 minus a1x, and that thing whole squared. So that is the error over here. I mean that is the least square error. And now because we want to minimize that, so what we will do is that we'll find the derivative with respect to a0 and also with derivative with respect to a1, and we will set that to 0. And after setting those to 0, we'll make some algebraic manipulations, and then we come up with this equation, these two equations. That is a0 into n, where n is the number of data points we have. So for over here, for the example that we have taken, so the number of data point is 1, 2, 3, 4, 5, 6. So over here, capital N denotes 6. So a0 n plus a1 summation of xi means all the data points that are available in xi, sum of them, and this equals to summation of yi. Also like portrayed through matrix, where this is the n summation of xi, summation of xi, summation of xi square multiplied by a0 and a1, and these are the coefficients we want to find. So which is equals to summation of yi and summation of xi yi. Now if we want to find a0 a1, what we can do, I mean we can take the inverse of this matrix. Let's say it is matrix A and this is matrix B. So a0 and a1 will give, I mean we can find it by inverse of matrix A into matrix B. So that will give us the values a0 and a1. And note that inverse of A into B will give us a 2 cross 1 matrix. That is 2 rows and 1 column, and it will have, the first row will have a0 and the second row will have a1. So now we will go into MATLAB and code this. So actually I have already created the data points beforehand, so that there are no issues. Let's give it the name linear least squares. Okay, it's taking some time. Okay. So these are the data points that we are talking about. So I've already created them beforehand. So now we will start writing the code for the linear least square. So before that, let me plot these two things, these two data, x and y. And let's say we want to use blue squares. So let's run this once. So you see, okay, these blue squares denote the data points that we already have. And we will try to make a best fit line for these points. Okay. So we also have to find the length of the given data points, I mean the matrix, length of the matrix of the given data points, because we will be needing, as we said that we will be needing n, the number of data points we have. So let's say n equals to length of x, or you can say y also, I mean it's the same thing. Now we will go to linear least squares. So now we'll be creating the matrix A that we were talking about. So what is the matrix A? It has a capital N, summation of x, and summation of x square. Now this x square means, I mean, it will be 0.64, 1.96, something like that. Okay. So the first will have n, the first row, first column will have n, then it will have the summation of all the data points at x. Then we'll go to the next row. The Second row, first column will also have summation of x, and the second row, second column will have summation of x square. I mean the like it will have 0.64, not the square of this matrix X, but the square of the data points. So once again, we'll be using the dot for getting this thing, because if we simply do the square of this will not be an appropriate one, or neither can we do a multiplication also, like x into x, because this is I mean like multiplying 1 2 3 4 5 6 7, so 7 cross 1 into 7 cross 1 will not give the, it's not possible, so we have to use a dot. Instead of the power, we can also use a multiplication symbol and the x, because that also denotes x square. So we have created our A matrix. Now we will be creating our B matrix. So our B matrix is summation of yi and summation of xi yi. Now xi yi means 0.8 into 0.69, 1.4 into 1, 2.7 into 2.02, something like this. So which will again require us to do, again require us to use the dot. Now we are going to the next row, because this is a 2 cross 1 matrix. So it will be sum of x into y. Okay, let's at first, we have already initialized our x variable. So let's evaluate this selection, what it gives us. So that's exactly what we wanted, 0.64, 1.96, 7.29, and so on and so forth. Okay, let's do it for x dot y also, whether it's giving the correct thing that we want. Okay, 0.8 into 0.69, it's actually the right answer, but another one we can surely check is 1.4 into 1. So that is 1.4. So we're going in the right direction. Okay, so now we have to find the coefficients. So as I said that the coefficient matrix also will be a matrix of 2 cross 1. So let us call it phi, and it will be inverse of A matrix multiplied by B matrix. Now we were wishing to find A0 and A1. So the A0 will be the first element of phi, and A1 will be the second element of phi. Okay, so let's run this. Once again, it will give us the same plot, but let's look at the values of A0 and A1. So A0 is coming as 0.4375 and A1 is 0.4698. So these are the coefficients that we have got. So now let's us try to plot a straight line. Oh, before that, let us look into the earlier plot once again. Look, this plot is ranging from 0.5 to 5. So we will also range our values from 0.5 to 5 and see what does the plot look like. So let us hold the earlier plot, because we want to fit a straight line above it. And let's say we will plot, let's say our first point is 0.5 and second point is 5. In between this range, I want to see a straight line. So sorry, 5. So next will be A0 plus A1 multiplied 0.5 and 5. And let us give it as dotted lines, 2 dotted lines with a red color. Okay, so let's save it and run this. So you see this. So this is the best fitted line that we can get using linear least squares. Okay. So this was a numerical method. And apart from this, MATLAB has its own function that is called LSQ curve fit. So over here, what we have to do? We have to provide fname. Now what does fname means? In fname, you have to provide the model. It is the Y model. Like what should, I mean, like what do you want actually? I mean, what is the equation of the model you want? So for our case, it will be a0 plus a1x, means that's what we want. And p0 is the vector of initial guesses. Over here we have to give some initial guesses, and x data and y data is the data that we already have with us. Okay, and phi is the answer that we will get. So what this LSQ curve fit does is that it minimizes the error between the y data and the model, and the data that we have and the model that we are giving. So let's go back. So let us create a function for providing inside the LSQ curve fit function. LSQ curve fit function. So we will firstly initialize fi comma x. What this fi is? This fi is the matrix under which we will have the two data points. So and fi of 1 is a over here, and fi of 2 is b, or a1 as we have said, into x. So this is our model, isn't it? It was actually a1, a0 plus a1 of x, and we say that let's say that phi is, I'm giving a variable, independent variable phi, and which is a vector matrix, and the first element of the vector matrix is phi of 1 is a0 and phi of 2 is a1, and that was actually the model a0 plus a1 of x. So we are done here. So now let's find the answer. Be f, the function name. Now we have to give some initial guesses. Let us give initial guesses of 1 and 1, and then we have to give the data points. So x at first and then y. So if we run this, okay, let's we have seen the plots. Let us comment them so that not every time it does not run itself. I've done something wrong, I presume. Okay, what I've okay, am I audible now? I mean, I think in between I lost some connection.
Yes, yes.
Okay, what I did a mistake over here is that I did that at the rate of I mean, it should be at the rate fi comma x. Oh no, sorry for this. Okay, I have also did not give a semicolon here, so it has shown me the answer. So okay, anyway, it's good. So this has found the answer, and it is giving me the answer as 0.4375 as a0 and 0.4698 as b, sorry, a1. So it is exactly the same that we have got for using the linear least squares numerical method also. So hence we see that LSQ curve fit is a easier way to do this using the MATLAB function. So now let's clear this. So now we move on to the next question. I mean, like not next question, next topic, that is linear regression for multiple parameters. So let's say we have given a data as x1, u1, w1, and y1, and so on till n points. And we want to fit a model that's something like this: y equals to a0 plus a1 of x plus a2 of u plus a3 of w. And this can extend also. It's not that it's limited till here. I mean, where there are multiple parameters. So what we have to do in front of one for like n times, and then the coefficients with a1 is x. I mean where x is like x1, x2, x3 dot 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 up to xn, and so on, like u1, u2 dot dot un, w1, w2 dot dot un. So wn, and this is multiplied with the phi matrix which has the coefficients. A0, A1, A2, A3. So if I multiply it with this matrix, that will be A0 plus A1 of X1 plus A2 of U1 plus A3 of W1, and so on. And it will give us Y1, Y2, dot, Yn. So what they have done is that they have created this matrix and they have called this X. And this is the Y matrix that is called as capital Y. And for getting these coefficients, so we have to do something like this: X transpose into X, and the inverse of it multiplied by X transpose into Y. So now we will take a question and we will try to solve this. So we have X, U, and Y. And we want to fit a model which is like this: Y equals to A plus BX plus CU. So let us go back to MATLAB. Once again, I have already created the data points under regression, under linear regression, multiple. So as I said that for the multiple regression, we have to create, that's also very simple. We just have to create two arrays. One is capital X and one is capital Y. And then as per the formula that was given, we can find the coefficients. So, and also we have to calculate the length of the data points. So let's start multiple regression. Our capital X array will be the first column. No, sorry, the first column will have, because we're trying to fit a data that is A plus BX plus CU. So the coefficient with A is 1, and the coefficient with B is X, and the coefficient with C is U. So the first column will have ones. I mean, like 1 for 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And it will be a 9 cross 3 matrix. So the first column will have all ones. The second column will have all the values of X in order. And the third column will have the values of U in order. So we can do this by using the next, this is we're going to the next points of X, and then we'll give the data points of U. So this is our capital X matrix completed. Now we will have our capital Y matrix, which was nothing but the data points of Y. Now for finding the coefficients, the formula was something like this: X transpose into X, the inverse of that multiplied by X transpose into Y. So it's very easy. We'll first use the inverse X transpose. This is known as X transpose in MATLAB, multiplied by X. I mean the inverse of this under this, multiplied by X transpose once again, and multiplied by capital Y. I mean Y also would have done, but we have already initialized capital Y, so let's go on with this. So this will give us the phi matrix. And the phi matrix it will be a 3 cross 1 matrix, and the first column and the first element will be A, and the second element will be B, and the third element will be C. So I'm not suppressing the ego. I want to see the answers. Okay, so it's done. So for this question that we are seeing in the slide, we get a equals to 11.8391, B equals to minus 2.7952, and the C equals to 6.7543. So this is all for the multiple regression. Now let's clear this. Let's go back. Okay, so now we'll be looking into nonlinear equations, nonlinear regression. So let's say we have an equation something like this, where the mu equals to km capital C by k plus root of c. And the question has stated us to use the initial guess of km as 5 and capital K as 1. And these are the data that we have been given. Capital C and capital C and mu, where capital C is the concentration and mu is what is mu? Growth rate. Okay, so there are two ways to do this. The first way is to use the MATLAB function LSQ nonlinear. Now this function, to use this function, you have the optimization toolbox installed in your MATLAB. So like when I had installed my MATLAB 2016 when I was in the campus, so it already had the optimization toolbox. But for the MATLAB 2020B, it was not there because I was in my home, and presumably I did not install all the toolboxes. So you have to I mean look into it, whether it is installed or not. If it's not installed and you try to use it, it will give you it will say it in the command window that you don't have it installed, and they will show you the path also, like how to install it. So it's very easy. It will only take 5 to 10 minutes to get it installed. So there is no issues with it. And even if you find issues, I think you can use the online MATLAB, and you can do it easily there. Okay. So now we'll be doing the nonlinear form of regression. So once again, I have created the data points from before. Let's go back once. So this is the capital C and the concentration matrix. Now in the equation that we have, we will also require root of C. Okay. So let's do that. Let's find the square root of C. Now once again, we have to use, okay, let's do square root of C. This will give us the root of C. Now let us use LSQ non-linear. Oh, we have not talked about the syntax of LSQ non-linear. Let's talk about that. So this we have to provide a function name, and this is the independent variable, and the p naught. The p naught is the vector of initial guesses. Now what we have to provide in the function name, it will provide we have to provide a vector of errors. That is, let's say our function, we have a function and we have to provide the function name as an error. I mean, the expression should be the error of the model we have. Like for example, over here, our mu equals to this thing, kmc by k plus root of c. So the error will be mu minus of kmc by k plus root of c. So this will be our error. And we have to create a function, something like that, that will express the error. So at first, we have to create that function. Now, for the function that we have to create, we don't know the km and the k value. So I'm taking the phi of 1 as km. I mean, I will initialize with, I'm taking an independent variable that is phi over here. And we have these constants already with us. Not constants, actually, these are also variables, but we have it with us. So we can use it in the expression. So it will be something like this, mu minus of, as I was saying, it is mu minus of kmc by k plus root of c. So the phi we have taken in the function we want to create, it has km and k value, and we are taking the km as it is in the first element of the phi matrix, and k is at the second element. So we will write phi of 1 into capital C. Okay, so we will have to use a dot over here because this will be an element-wise element matrix operation, and then a dot divisible by phi of 2, that is capital K, plus square root of C, which we have already created as root C. Okay. So now we are done with the function. So we have already created the function. So, and the question also stated that we will use initial guesses of km as 5 and k as 1. And as I said, km was the first element in the 5 matrix we have stated. We can also do it different ways. Okay, you can also like take k as the first element and km as the second element. So there are no restrictions with that. But then if you are taking km as the second element, then you have to write phi of 2 and you have to change this as phi of 1, something like that. Okay, but I'm taking this as phi of 1. So let's move ahead. Okay, so now we will find the coefficients by using the nonlinear function. So the function is already created by us. Now we will give the initial guesses. And the initial guesses also has to be with the in relation to how you have put the data, not the data actually, this phi 1 and phi 2, because my phi 1 is km here, so I'll have to put the initial guess of km first. What was my initial guess of km? It was 5. So 5 and 1, these are my initial guesses. Okay, so this should give me the km and k. Once again, we'll find this like this, and capital, let's call it capital K. Okay, let's not suppress the equal, let's see the values. Okay, once again there is some issue with the MATLAB and the function I created. Okay, I've spelled it wrong. I'm sorry for that. So okay, so after using this MATLAB function, so what it gives me is that km as 5.8350 and capital K as 1.9272. So there's another way of doing this equation, this problem, and that is if we convert this nonlinear equation into a linear one. What we can do is we can just do 1 by mu, then it will give something like this. Then it will be k plus root of c divided by kmc, which will give us something a constant value by 1 by c plus b into 1 by root c. We can write something like this, isn't it? And where a will be capital K by km and b will be 1 by km. So what we can do over here is that we can create separate matrices. Like now this is our y, let's say, and this is our vector x 1 by c, and sorry 1 by mu is let's say 1 by mu is the vector y, and 1 by c is our vector x, and 1 by root c is our vector, let's say, u. And as we had seen the problem with multiple regression, that you can create a vector capital X, which will have the coefficients, not the coefficients, I mean the elements associated with the coefficients, isn't it? Like we saw this in this case, this one. The numbers associated with the coefficients like x, this is how we had created the capital X vector. So once again we can use this expression to get a solution, but note we will be getting a and b, and from that we will have to calculate km and k. Like if we get b, we can calculate that km equals to 1 by b, and if we get km, we already have the a value by using the multiple regression, then we will get km. So let's do this. As I was saying, let us the 1 by c, let us do it as x, and let us say u equals to 1 by square root of c, so 1 divisible by root of c, and the y will be 1 by over gamma. Once again, the dot is for element wise element matrix operation. A simple 1 by a matrix is not possible, but we actually want, let's say, this mu1. What we want over here is 1 by 1.16. So that can be only done through this dot operation. So that is why we are doing that. Okay. So now in the x vector, the capital X vector, we will only have x and u, because these are the things associated with the variables. I mean, with the constants, the constant coefficients, isn't it? Like with A, we have 1 by C, and which we have said it to be x. So we'll have to provide the values of the x vector. And for the second column that are associated with the coefficient at B, that is 1 by root C, which we have said it to be u. So we'll have to provide these values into the capital X form. And we can write capital Y as Y. And once again, we can find this function, I mean, like the answer using the equation that we had already done, that inverse of x transpose into x multiplied by x transpose into y. What can we call this? Let us call this ln 5.
Hello, Suman.
Yeah, hello. Hello.
Hello.
Yeah. Am I audible?
Line 17. Is it root C correct?
Yes,
Or
it's correct. What do you think is wrong in this?
means the command of square root is sqrt.
No. See, so command of square root is square sqrt, but we have, I mean,
Okay.
put the value of square root of c under the variable name root of c. That's why I've used root of c.
Yes, sir.
Okay. So already we have created this square root of c. We have given it the name root of c, root c. So that is why I have used root c. You can
Yeah,
also
yeah.
use this thing also. I mean, instead of this, you can also put this thing. There are no issues with that.
Okay, thank you.
Okay. So now it will be inverse of x transpose, capital X, into x multiplied by x, multiplied by x transpose once again into capital Y. So this is the equation that we have already done for multiple regression, right? So once again, we are using this while we are converting nonlinear to linear as well. And this time as well, we will get the values, but this time this ln phi will give us these values, that is a and b. And to get km and k, we have to, we have to make some algebraic manipulations to do that. So as you can see that this b will be the second element of this ln phi. And for getting km, we have to multiply, sorry, we have to do 1 by this b. And because this b is the second element of ln phi, so my km, let's say km1 here, will be 1 over ln phi of 2, because the ln phi of 2 gives me the b element, the element b. Once again, I will not suppress the echo. And for getting capital K, let's say 1, because we have already created one capital K. So this will be using linears, a linear form. So let's look at this. So for getting K, capital K, we need to have the value of A. So that we already have from the ln phi function. And the ln phi function, first element of ln phi function is my A. And we have already, before this, we have already found the value of Km. So for getting K, we will have to multiply A into Km. And my A is the first element of ln phi multiplied by km1. You have to be very careful with these variable names, because we generally tend to make mistake, but once we see it, we can correct this. So let's run this. So now what we are getting is, we are getting a km1 as 4.9173 when we are using, when we are converting the nonlinear to linear, whereas in the first case we got a km of 5.8350. And for K1, we are getting 1.4465. Whereas in the earlier case, using the function, the MATLAB function, we got 1.9272. Okay. So this is how you do a nonlinear function, a regression of a nonlinear function. And if you want to convert the nonlinear function to linear one, you can use this method of multiple regression. So now I'll clear this and we'll move ahead to the next topic. So next is interpolation functions. So MATLAB has various functions for interpolation, but today we'll be looking into spline and p-chip. So spline is also known as the cubic spline interpolation. What it does is that given us data points, it gives us a smooth curve. I mean, it tries to create a smooth curve for that given data points. And p-chip is known as the piecewise cubic Hermite polynomial. It also creates, it also tries to cover the data points with a curve, but it is slightly different from the spline. It's not smooth. It tries to keep a monotonicity with itself. So that we will learn when we will do the plotting. And the syntax for this is that, so this is the interpolated values we get using spline. The spline is the MATLAB function. So you have to give the data points. Firstly, the x data and y data is the data we have. I mean, like suppose we are given some data and we want to interpolate other data points. So the x data and y data is the data point that we have been given. And xval will be the values, the points for which we want to get the interpolated function. Let's say I have a data that varies from 0.2 to 2, but there are not all the points between them. So I may write a 0 to 2 over here. So that's what xval does. So I'll create I can create a vector from 0 to 2 in this for xval. And the syntax is similar for p-chip as well. Just instead of spline, I have to put p-chip. Okay. So we will try to do the interpolation function with these data points. So this is an example of a vehicle speeding in front of a government hospital. So at this point, this is the starting point at 0. It has 45 units not given. Let's say kilometers per hour. So it's running with 45 kilometers per hour, and then from 20 to 30 it has stopped. Actually, there is a signal in front of the signal, so it had to stop for a few seconds, and then it again started running. And at the end of that is 90 seconds, it again reached 55. Its speed of 55 kilometers per hour. Let's say. So we'll try to interpolate the values in between them. I mean, what could be the value at let's say 5? It's 25. I mean, at 25 it should be 0. Let's say let's see what the different functions that we have, what values do they give. Okay. See the name I have created for this. Okay, so the spacing for the time for the data was 0 to 90 with a spacing of 10 seconds. So I've already created the data where t is spacing from 0 to 90 with a spacing of 10, and this is the speed that was given. Now we will try to interpolate them. So before that, let us plot these data. It's a blue and a circle. So this is the data point. Let's give a hold on because we will be plotting again. Now we will use interpolation using spline first. So now let's say we want to find from 0 to 90. So we want to find the interpolation, or time interval. Let's give it from 0 to 90. Sorry. Note if I don't give any, the interval in between this, then it will go for with an interval of 1. And if I don't set any interval for going from 0 to 90, the default is 1. So my time vector will go from 0 to 90 with a spacing of 1. Now I want to find what should be my speed in these times. Let's call it SI spline. Now we will use the spline function. So as in syntax we have to give the data points first, the time vector, the already given speed vector, and the vector for which we want to find the speeds. So this is our TI. So this will give us the speeds at from 0 to 90. Now let us plot this. Now we will try to plot from 0 to 90 with a spacing of 1, because we will do it for all the points between 0 to 90. And for the 0 to 90, we have the speeds, that is SI spline. And let's say we will be using a black line to represent the spline function. Now let's see what happens. Okay. So these were the data points that we have had, this circle one, and this is the curve that spline is giving us. But note one thing, see this is 0. I mean, between 20 and 30, the car was at rest. So naturally, I mean, according to physics, or as we know, that the velocity cannot go below 0. But what the spline function does is that it always tries to create a smooth function, and it does not keep its surroundings into result that because this and this was at 0, it will keep a straight line. So it basically tries to create a smooth function. So that's what spline does. Now we will go and interpolate using p-chip. So the time vector is already created by us, that is from 0 to 90. The only thing we have to do is we have to create the speed vectors using p-chip. Let's say SIPC. The syntax is same. Just use p-chip instead of spline. T, S are the data points we have, and we want to find them speeds for the TI vector we have created. And once again, we will plot the TI vector from 0 to 90, and this time with the speeds using the p-chip. And let us give 2 dotted lines and the red color. And let's see what happens. Okay, so now you see that in between 20 and 30, what p-chip does, it maintains the 0 thing. So that should be the real graph for the case we have been looking into. So what is the main thing of p-chip is that it tries to maintain a monotonicity. Like look at this thing, these 2 points, it's decreasing from this point, and it is not going above this point. Okay, because this point was below this point was below this point, so the curve is always in a decreasing mode. And for these 2 points, because this point was also at 0 and this point was also at 0, so it has kept a straight line. So it tries to maintain this monotonicity between the 2 points. Whereas for a spline, it tries to create a smooth curve. So they both have their implementations, and according to the situation, we have to use what we want. Okay, so this was it for the regression and interpolation. So do you have any questions?
Hello.
Yeah, any questions?
Yeah. I want to know, like, actually, the syntax of spline is not clear to me. It is T, S, Ti.
Yeah. So like T, S is the data points that we have been given. Like say we have been given a data point, and we want to find the interpolation. Okay, so this is clear, right? T, S is clear. Like we have to give those to the data points that we have been given. And for this Ti is like the range in which you want to find the data points. Like because in between, although this is between 0 and 90, you don't have the values for each second, right?
Yeah.
Let's say for one second, you don't have it. You have for 0, 10, 29, 30, and so on to 90. So what I have done is I have created a variable called Ti. So if I look into Ti, what it is, so it is like 0, 1, 2, 3, 4, 5, 6. I have created a time variable which goes from 0 to 90 with a spacing of 1. So I want to find the speed at all these points. So that's why I've created this Ti, and I'm putting this Ti. I mean, this is the points at which I want to find the speed. So I'm putting that thing over here. These are the data we have, T and S, that is given to us. And this is the vector of data where we want to find the possible value of the function that we don't have with us actually. Okay, did you get this?
Yeah.
What it is?
But I want to know, we have created 90 points, okay?
Yeah.
To know the speed at these 90 points, 0 to
Okay.
9.
Let's see
So
for spline and speech.
it is a stored, yeah.
See, for the spline one, the first
Yeah.
was 45. And so it's going on like that, okay? For each
Okay.
data point that we want. Now you can also change it. I mean, you can change the time interval also. Okay, you can give a spacing of 2 also. So it will go from 0 to 2, 4, and so on like that. And then the values will be a little different, but you get the point. For the PCHIP also, it's doing the same thing. I have given it a vector of values where I want to find the interpolated values, and it's calculating them.
Okay. Okay, thank you.
Okay. So another thing I wanted to say was that, I mean, you guys might have noted that I am not using this editor for running them. So there is actually a shortcut keyboard that you can use. You can use Control and Enter. That will give you the you can run a code through that also. So that comes in handy if you are working for a long code. Okay, any more questions? Okay, I don't think so. There are more questions, and this is the end for the regression and interpolation. So should I stop sharing now? Hello. Okay, then so I'm stopping my screen share, and that was it for today. And thank you everyone for attending the session.
Thank
Okay,
you,
I
sir.
have something in chat. Okay, at 6:21. Was there anyone's question like this related to anything by Nalanda Vidya? Did you have any question? Because you said something in the chat. Okay, then so I'm ending the session over here. Once again, thank you everyone and have a good day.